Human vibration and long-term exposure in high levels can have a lot of negative health effects, especially if you're working with tools, but it also goes for people who are long-term driving trucks and cars. Lots of sustained vibration can do a bunch of different things. So here on the left, there's a picture of somebody with fingers and they're turning white. This is called white finger syndrome. This is because vibration has slowly killed off the blood vessels that connect to the fingers, so you get a loss of blood and you also get a loss of sensation. You get some nerve damage. This can happen for prolonged exposure hand-arm vibration. It can happen if you're driving a truck and you've got your hands on the steering wheel and the steering wheel isn't properly damped. Another thing you can get is a lot of nerve damage to the spine, severe nerve damage, especially in the lumbar region if you're undergoing whole body vibration. I know that NASA in particular looks at whole body vibration for astronauts and rocket ships because it can have negative effects during takeoff and landing. Short-term exposure, you can get things like headaches, fatigues, insomnia, slower reactions, like brain fog if you are short-term exposed to a lot of vibration. So these are really important, and the European Union got together and decided that they wanted to create some standards to make sure that products that were going out weren't affecting consumers, especially if you're in the trades and using tools every single day or you're driving every single day. So that's why we actually look at human vibration. So there's two types of human vibration. There's whole body vibration, which I feel like is kind of self-explanatory. It's the vibration that's being imposed on your entire body. And there's a couple orientations that really matter. And the reason they matter is because the body is sensitive in some directions more so than others. So in the Z direction, the up and down position, the body's actually slightly less sensitive than it is in the X and Y. The X and Y matters a lot more on the person. So later on in the presentation, you'll see that there are more health factors associated with the X and Y directions for whole body vibration. There's also hand-arm vibration with the Z direction going along the side of the arm. I'm not sure if you can see my mouse, hopefully. This hand-arm vibration, this is typically done for people, like I said, who are using something every single day with their arm. So my industry example is tools, if you're using a power tool every single day. Strangely enough, that the European Union decided that there is not an orientation for the hand and arm that is more important than others, so all these are all weighted equally. But it's really important to measure in all three directions because it absolutely can affect you, and it does matter. And we usually look at the summation of all the directions anyways. This is one of my favorite things over here, this weird robot-looking guy. This is a dynamic systems model of a person, and there's kind of these resonant frequencies that people have guessed that they've modeled people after. And you'll notice that a lot of these are really low frequencies. And that's going to be important too, because some frequencies affect the body more than other frequencies. And there's weighting curves. So if you've ever done anything with sound, you may have heard of A weighting or B weighting. They're curves that are applied to sound because some sound affects humans more than others. It's the same exact thing for vibration. Some vibration frequencies affect the body more than others. And so we kind of account for that with our weighting curves. A lot of them are ultra low frequency. So here's some of the vibration curves here. We've got whole body, and there's these WKs and WDs, and I'll talk about that in a second. But there's whole body vibration for the Z direction. That's this blue curve here. So from about 4 to 8 hertz, that's where people seem to be the most sensitive. And then anything after that, as you get higher in frequency, we can attenuate the signals. Humans aren't as sensitive to these frequencies. Once you get really high in frequency, then your body's pretty good at absorbing that vibration and it dies off. So this is for the whole body. And today, most of my examples are going to focus on hand-arm because that's the data that I have. There's another thing here called motion sickness. I'm not going to talk too much about it, but if you are in the marine industry, for example, and you want to be able to predict if somebody's going to get motion sickness from your product, this might be a curve you might be interested in. There's a couple equations that are later on in the slides that discuss this a little bit. So this is what the hand-arm weighting curve looks like. So it's a little different. So there's a bunch of different curves, and luckily nobody needs to memorize these. These are all built into TestLab if you're doing this in TestLab. So that's really nice. But it's important to select the right curve because you will get different results. They are different curves. How they came up with these curves, I'm not entirely sure. I think it was a trial and error data because this occurred a long time ago. But make sure you're selecting the correct curve. The general data when you take it, so I have some data here. There's I was playing a very popular video game, and I got into a battle with a dragon, and the controller starts shaking a lot. So the red will show the unfiltered data, And then the blue shows the filtered data. So I filtered this using TestLab through the human body vibration filter for hand-arm. And you can see that the amplitude has decreased before the calculations are performed. That's because, once again, the human body will attenuate a lot of that vibration. The general process for doing vibration data is you have an accelerometer. You usually want to put it somewhere near the test article that you're interested in. So when I did hand-arm vibration on the tool, I would put the accelerometer right where the hand would grip, so we could get an accurate measurement of that. If you're doing whole body vibration, there's special pads where you can put these accelerometers in so that somebody can sit on them. They're like seat pads, if you've ever heard of those. So you get an accelerometer, you take a time history, then you weight it with those curves we just showed, and then you get a weighted time history. And then from the weighted time history, there's a ton of different things you can do and a ton of different metrics, and we will get to that. The most basic metric is what we call AW. That's your weighted frequency acceleration. So this is the acceleration data that's been passed through your weighted curves. And you can kind of think of it like an RMS value. That's typically what we look at when we're looking at human vibration. We're trying to get a total value to try to compare it to something else, usually a singular value. So if you wanted to get it in all three directions, you could calculate AV, V standing for vector, very scientific, and it's just the square root of the sum of the squares. If you're wondering what these Ks are, that's because earlier I mentioned some directions have different weighting factors than others, because some are more sensitive to the human body. So for whole body vibration, the X and Y direction actually get a factor of 1.4. The Z direction just gets a 1 factor. So it's important when you're calculating these frequency weighted acceleration values, if you want a total, and you're going to see this in TestLab too, this vector sum, we're going to use this a lot to calculate the overall level. This is how you calculate it for all three directions. There's something called the maximum transient vibration value. This is the maximum value of all three directions of your A weighted. So you've got an X, Y, and Z direction, and this is the maximum value of that. It's very easy to calculate. And if you're wondering why we calculate AW and MTVV, and there's something called vibration dose value, the reason is AW is really good for stationary, steady state style data. This is data where you're not getting a lot of sudden impulses and peakiness. And if you do start to get impulses and transients and peaks, there's a different metric to use for that. But to know how to use the right metric, to make sure you're using the right metric, we can calculate MTVV, this maximum transient vibration value. And this value will tell us whether or not we need to use this A-weighted RMS value or some of these other vibration values down here. These are more used to diagnose which type of value you should be reporting when you're taking this data. Okay, for whole body, you saw that there was a WK, let me go back a little bit. There's a WK and a WD. WK is whole body vibration in the Z direction, and WD is whole body vibration in the X and the Y direction. So there's reasons why we measure them separately. It's mostly because they have differing effects. For hand-arm, we have something called AH. You might see it as AHV. AHV is the summation in all three directions. This is that curve WH, AH. There's another slide with all the jargon in case you forget. These ones don't have a special call-out between the directions because these are all weighted the same. There's something called AH equivalent 8, or the 8-hour exposure limit. So this is if you're trying to see if something's safe for somebody to use for an 8-hour workday. So like, let's say you're a tool company and you want to make sure that your jackhammer is safe for somebody to be using for 8 hours a day. You can type in your acceleration values that you measured over the time that you measured it, and then divide by the amount of seconds in 8 hours, which comes out to roughly like 29,000. So that's one way you can calculate your exposure limit. There are comparative values for what is safe and what is not safe to find in these ISO standards. Up next is something called crest factor. Crest factor really just tells you the peakiness of your data. It does that by dividing the peak amplitude over the RMS value, specifically the weighted peak amplitude, and I'll show you how you can make that mistake really easily later when we're going through TestLab. But if you don't use the peak amplitude, the comparison number isn't going to make a whole lot of sense. So the crest factor is a really good way to tell if you're getting a lot of transients in your data. If you're getting a lot of transients in your data, you might want to use this vibration dose value. This vibration dose value is separate from this frequency weighted acceleration. These two values are typically what you want to report, and this is specifically designed for data that is more transient. The equation's a little different mathematically, and it's for a good reason. So here's another example of whole body vibration. We've got some guy in a truck, If you were to measure this, you might measure the steering wheel, you might measure the seat pad, you might measure the back of the chair and the feet. There's a bunch of different positions. So that vibration dose value, once again, this is used if you're doing very impulsive transient data. This is calculated a little differently than the other equations because it's brought to the fourth power. And the reason it's brought to the fourth power is because the fourth power is more sensitive mathematically to spikes in your data. So to amplify those spikes in the data, to make sure that we're staying below important limits while reflecting the important transients in data, you can use this vibration dose value. It just amplifies it to the fourth power, and then we take the quartic root of that data to get it back to normal. So there's two different ways to calculate it here. These equations are for reference. TestLab calculates these for you. You don't need to worry about it. You can do a total summation in all directions, but typically people will report the VDV of the highest direction. We talked about when to use different metrics. If your MTVV, that's that transient method, the maximum of your A-weighted acceleration, if that value is greater than 1.5, you're going to want to report this value. Your data is too peaky to be using this stationary RMS value. If your data is 1.75 times the A-weighted times your time, you're going to want to report this VDV total value. That crest factor is also used as a measure of peakiness. You can use that too. So if your crest factor is less than 9, you can use AW. And if it's greater than 9, you're going to want to use that vibration dose value. So this is a measure of peakiness. If it's below that, you can use basically your stationary. If it's above that, you're going to want to use that metric that's more sensitive to those transient impulses. And here's another example of white finger syndrome from somebody who's prolonged use of a tool over a long period of time. So hopefully that makes sense. And if you forget, here's a beautiful chart right from the Siemens website that sums up all of the weightings. So WK, WD, there's a bunch of them we didn't even talk about. WJ, which has to do with your head position. WC, which has to do with your back position. But mostly for this presentation, we're going to be focusing on WH, that hand arm. So there's two standards that are used. It's important to remember these just because when you're in TestLab, you will have the option of picking either one to filter to. And if you filter the wrong one, as we showed earlier, those curves are different, you will get the wrong answer. So there's ISO 2631. This is the one for human vibration. Once again, WK and WD. And then there's ISO 5349. This is what we're going to be dealing with today. This is the one for hand-arm vibration. And then at the very bottom, there's a little motion sickness equation that's also covered in these standards. So I threw that up there for reference. I mentioned that we're trying to get singular values because we want something to compare to. So when the EU made these standards, they have some take action limits and some immediately stop limits. So for whole body vibration, if you take the vector sum of your A-weighted data, if you report the VDV value or the AW value, if it's above 0.5
meters per second squared,
you need to reduce the vibration. Or if it's above
1.15 meters per second squared,
you should stop. For vibration dose values, this is closer to
9.1 meters per second to the 1.75 power and 21 meters per second to the 1.75 power.
If you're doing hand-arm, your reduced vibration action is
2.5 meters per second squared.
And that's actually pretty low. So most of the power tools that are designed for people who work in the industry, most of the time the handle is actually decoupled from the rotating mechanism in an attempt to reduce the vibration. The exposure limit, the stop action exposure limit for this is
5 meters per second squared.
Another thing you can do is you can take your total value and you can take that 8-hour exposure and find out if you are going to be at risk for white finger syndrome. So there are specific charts that exist out there specifically to predict whether or not somebody will get white finger syndrome. They're not 100% exact. Everybody's a little different, but it's a good predictor chart to see if your product or tool will affect people negatively. So for whole body vibration, the general process is to measure the data, and then in TestLab, these two steps are done together where it filters it into octave bands and then it weights those octave bands because there's specific weighting criteria for each frequency. And then you'll have it in 3 directions. You'll have your A-weighted and your X, your A-weighted and your Y, and your A-weighted and your Z. You can do the sum of the squares. This 1.4 is that health factor that gets multiplied. And then you can get a total vector, this AV vector. If you want to do an 8-hour exposure, you can apply the AV vector and multiply it by your T, which is the time you took the data for, over T naught, which is the time, the seconds in an 8-hour day. For hand-arm, the process looks very similar. We're going to weight the data. The data will come out in 3 directions, and then we're going to do a vector sum to get the overall level. And this overall level is what we're going to be able to use to compare back to those EU standards. The math behind most of what we're doing is actually really, really simple. It's the weighting and the filtering that gets more complicated. But luckily, I will not be weighting and filtering by hand today. I don't know anybody who likes to program filters and Butterworth filters by hand, but that's not me. So we'll be doing that in Test Lab. So for my data, my setup was very simple. I had a little Scadis XS. I did this data at home. I connected my accelerometer. It's in a very specific position. This position is because when you're playing video games, if you've never played video games before, there's these little rumble pads that are inside, these rumble motors inside the controller. They give haptic feedback. So I battled in this video game 2 different bosses. I battled a troll and a dragon, and as I'm battling this troll and dragon, this controller is starting to shake and go crazy to let me know that the dragon has landed, or I've landed a hit, or I'm being hurt. So in video games, this can be pretty useful to players. And I just wanted to see exactly what the acceleration values were, that if I was playing this 8 hours a day. So here's my 2 battles, and I'll show you the data too so that you guys get an idea. But I've got a troll battle and I've got a dragon battle. And if you know the popular video game, that's great. It's a fun one. And they're also taken at different, this data is taken for 30 seconds. This data is taken for about 100 seconds, because that's about how long I lasted in each battle. So now I'm going to pop it over to Test Lab. Okay, so I've gotten some measured data in Test Lab. This is just this is the throughput data in the X, Y, and Z direction. So I can zoom in a little bit. So all I've done here is plot my data, just so you guys can see that at some points I'm hitting a troll, or at some points I'm getting hit by a troll, and then my dragon data. And unfiltered, the accelerometer registered up to 31 meters per second squared. So this controller was shaking quite a bit during this battle for sure. The trolls actually only got up to a maximum of about 15 meters per second squared in any given direction. So that's what my data looks like. I'm going to post-process. We'll do post-processing 1. I'm going to post-process this Skyrim Dragon 3. So what I'm going to do is right-click and hit Add to the Input Basket. If you're new to Test Lab and you don't know what the Input Basket is, that's this thing right here. It's a little folder that lets you separate out all your data. So I had a bunch of data in my measured, but I only want to process the Dragon data, so I'm going to add that to the Input Basket. I'm going to go to Time Data Selection. I've already got these typed in here, but I'll re-type them in just so that people can get an idea. I'm going to add in my data. I've got my X, Y, and Z channels. Then the most important thing you need to do is you need to have the correct add-ins on. So for this one, at minimum, you will need, I passed it, human body vibration. If you do not have this turned on, those filters will not pop up in Test Lab, and you will be very confused wondering where the equation went. So this is important to turn on. I've also got Time Data Editor for the time data post-processing, and then I have something called, this is completely optional, but I did want to show you how to use data block processing. If you haven't used that, this might be a fun new test trick for you. So I've got my human vibration to add in. I'm going to add a new equation. I'm in the time data selection. So I've added my data from my input basket. If I scroll down to filter, there's 2 different filters here. There's the ISO 2631 and there's the ISO 5349. And the really easy way to remember them is the ISO 2631 is the human body, because it has a bunch of these tiny metrics in here that are all dependent on exactly where the orientation of your accelerometer measurement is. For hand arm, it's ISO 5349. That's what we'll be using. It says it applies the WH, H for hand. I'm going to click OK. My first channel, channel 1. And then I want to apply this to all 3 channels, you can hand type it in, or you can, if I'm careful about it, you can drag it down. Sometimes it don't like to work for me. There we go. So now it's applying to channels 1, 2, and 3. So my X channel is channel 1. I'll call this A hand X, A hand Y, A hand Z. And now I can calculate it. So I've got my 3 calculated areas, and this is good. We're pretty much halfway there. There's something really cool you can do right now too. If you want to find out If you want to calculate that MTVV and those crest factors, you don't have to go back to the navigator. You can calculate them right here to see what your next step needs to be. If you go over here to this hide additional pane and go to single value statistics, it'll pull this screen right here. Now I can add some functions. So I want to add in the max, because that's that MTVV value, and I want to add in crest factor. If I hit calculate, I now have them for all the channels. So remember earlier I said if you're using the unweighted, your crest factor is going to be really, really high. This is 63, that's way above 9, and that's not accurate. This isn't what our standards are built to. So if you look at your crest factor and it seems incredibly high, take a second and look at if you're using the weighted data, which is down here, or the unweighted data. So my unweighted data, I've got really peaky data in all three directions actually. I've got 8, 11, and 10. So hypothetically speaking, I would use the vibration dose value. So I'm going to show you how to calculate both of them. And then my maximum for the max, I can find out if my max transient value is higher using that little equation that was earlier in the slides. So obviously I'm going to keep going. After this has been calculated, you don't need to save it necessarily. You can go into time data processing. So I've got these 3 channels, and the weighted channels are the ones we want to calculate. So we want to make sure that those are selected. If you select these, you're going to get some weird data because this is unweighted. So my AAHX, my AAHY, and my AHZ. I'm going to go to channel processing. If you're probably used to seeing this screen, this is what it defaults to. If you go to derived fixed sampling, you can add a new channel with a function called vector sum. And vector sum, just like back in the PowerPoint, what TestLab's going to be doing is going to be applying this equation to your data. So we have our weighted data, and it's going to be applying this equation. So I'm going to do a vector sum. The important thing here is if you're looking at this side, it's a little misleading. It might look like the X is channel 2 and the Y is channel 4. To double check that you're getting the right channels, go to the source data dropdown, and we want channels 4, 5, and 6 because those are our weighted channels. So that looks good to me. I'm going to keep going. If I go to section, there's a bunch of different things I can add. So I'll delete these real quick and show you how you add them in. But I want to go to level calculation. Usually this defaults somewhere over here. I want to add the vibration dose value to calculate that. I will add the RMS equivalent sound. And let's do a running RMS. I'll just calculate all these. You can calculate all of them or none of them. It's up to you. But it's something to note. Another thing, this isn't part of this presentation, but there's also these vibration comfort metrics that can be selected. This is probably a different webinar, but I will point it out just because it's a part of the human vibration. So, and then the other thing I want to have selected is overall level. The overall level is going to be calculating this portion. So the vector sum is doing this portion, but the overall level is going to be doing the sum of the squares. It won't be doing the 1.4 unless you manually type that in. That's something to note for whole body vibration, but if you're doing hand-arm vibration, you should have no issues. There's a place later where I can show you exactly how to do that if you wanted to do it for whole body. So this all looks good. I'm in measured data. I should have been in post-processing, but that's okay. I'm going to call this demo, and I think I picked the dragon data. Let me double check. Out of this dragon, and I can hit calculate. So we can go look at that. Make a quick front back. Just got my demo data sections. If you hit this little icon up here, it'll open everything that's in that folder. So I've got my overall levels in all 3 directions if I want to look at those, and then I've got my overall level vector sum. Now this might not look super nice. That's because this is for the entire signal, but the value we want to report is an RMS value. So if I go to options, there's something here called calculated content. If you've never seen this before, all I did was right click on the cursor menu and go to options, calculated content, scroll down, and I want to grab an RMS value. I'm going to label that RMS so I don't forget, because I'm sure I will. And I have about 0.04 Gs. Our standards are in meters per second, so if I right click on this, I can change the unit. Now I'm at 0.4 meters per second. So that's good. This is really low, which is good. That's good to know. If I wanted to look at the overall levels in every direction, I can do that too. They're not as useful, I don't think. I can do also that vibration dose value for all three directions and see which one is highest. So in this case, the Y direction is the highest. Let's take a look at. This is like a running RMS, so you can do this a couple different ways. You can add the RMS value, or you can add the, there it is. So our last value in the running RMS is 1.41 meters per second, and the total overall RMS of this is 1.22. So this would be another value that you could report. So if my data was really peaky, which it is, and in this instance I might want to report the VDV value, and the VDV value, it's still below that 2.5 meters per second. I don't need to do any exposure for my data. There's another way you can calculate it. This is using data block processing. If you've never seen this before, this is really nice. You can actually manually go in and type in these equations. So I saved my data under measured data. There's different sections. I've saved it under measure, and I've saved it under demo dragon. I go to block processing. I can go to measured demo dragon and hit add. Got all these great channels here, and now I can manually do the vector sum. So if I wanted the overall level, the RMS sum, these are the weighted channels. This is what that vector sum did in time data processing over here, this vector sum here. So if I go to data block processing, I can manually type in F1, F2, F3 and take the square root of the sum of the squares, and I'm going to label that overall sum. I can also do an RMS sum. An RMS sum is the sum of the running RMS values, sort of like the vibration dose values I just showed you. These should turn out to be exactly the same. So this RMST, if you remember when I was in time data processing, I went to section and the level calculation I selected was running RMS. That's what this data block processing, what these channels are from. So I can do a summation of those as well. I can also, if I'm doing whole body vibration, this is where I can do square root of F1 times 1.4, F1 squared times 1.4, otherwise we're going to get some weird numbers, plus F2 times 1.4. It's weird. Sorry, my typing is off today. Plus F3. And these values came from those WD and WK, the health effects. So in the X and Z direction, I multiplied by 1.4. But there's none in the Z direction. Sorry, X and Y direction, I multiplied by 1.4. But there is nothing in the Z direction. So you could calculate that here, and I could call this whole body. This isn't going to make sense. This data wasn't taken for whole body, but we can calculate it anyways. So calculate. Another thing you can do is if you are running this through, there's a way to do this. We're doing the offline processing, so this is what happens if you've already taken the data. There is a way to automatically calculate all of this if you're doing processing during the measurements. So if you're physically taking measurements, there's a way to automatically calculate all of this so you don't have to do everything offline. You can also hit calculate automatically if you're doing a ton of runs. That'll also bring the data back into Navigator. So go here. And I've got most of this calculated, so in the interest of not showing you how to make graphs over and over again, I'm going to pull up some of that data. So this is the unfiltered data. This is the filtered data. This is the crest factor comparison between the dragon and the trolls. So I've post-processed both data now. And the way that I got crest factor is the same way I got those other metrics. I right-clicked, went to options, and calculated content. there's a statistical value called crest factor. I've labeled it and I have applied it. So for my trolls, my crest factor is really low, which is interesting. I would not use, probably not the VDV value for the trolls data, but for the dragon, it was pretty high, so I would report my VDV value for the dragon. Dragon data, I've got a couple things going on here. The overall sum and the vector level sum, these should match up exactly. They're the exact same calculation. Overall sum is the one I did manually in block processing. And the vector sum is the one that we selected when we were in the time data processing. So you can choose either one, whichever one ends up being more effective for you. So that data overlap is exactly the same. And my RMS value is 0.4 meters per second squared. This RMS sum, this is a sum of that running RMS. So you'll notice that it starts kind of high and then it slowly kind of levels off to the same value. This is an RMS over time. So at this point in time, it's an RMS of all these values. And at this point in time, it's an RMS of all the previous values. And it keeps going and it keeps going. So for the RMS sum, since it's a running RMS, what you want to do is take the last value. So I've labeled that here last value. And you'll notice that it's exactly the same as these RMS values. So that's another way, depending on how you would like to calculate it. There's a ton of ways to calculate it in TestLab. That's another way you can do it if you're running into issues or you want to make sure that all your data is lining up. Trolls data looks a little different. So here I've got my overall sum and my vector sum. Once again, these should be the same. They're calculated pretty much the same. And my RMS value is actually higher than the dragons. So the dragons had more peaks, more transient events, but my trolls level overall was a higher amount of vibration. And the last value, this blue is the running RMS sum. The last value matches up with these two values. And if you ever get confused and you decide later that you don't want some of this calculated content, you can get rid of it. So another thing I will show while I'm here is if I right click, it's really easy to lose track of all this data. One thing you can do is you can add in different things to the curve legend here. You can add in what the type of data that was taken. You can add in the direction of data. So if I only wanted to look at the X direction, or if I didn't label my directions and I wanted to make sure these were in the X direction, I can go to TestLab. It does not default to TestLab, but the origin should be set to TestLab. I can go to block, and I can start selecting how I'd like to label my data. So maybe I want to see point direction. So for these two, it labeled both of these in the X direction. If I want to name it, this is really useful. I have a bunch of curves up here. You don't know which runs they're from, if they're from multiple runs. I can go back to run and go down to name and add the name into. So overall, the processing steps in TestLab are very, very, very simple, but it can be kind of tricky to find everything and lose track of what you're doing. I know that I have a whole folder full of runs when I did this data because I was constantly losing track of what was the overall sum, what was the RMS level. So as long as you keep a good naming strategy, this can be really simple. But all you need to do is go in, filter the data in the time data selection, and then you can either use time data processing or data block processing. I like data block processing only because it gives you a lot more freedom after you've gone to time data selection to do different calculations. But time data processing will also give you that VDV and the running RMS. So just depends on the type of calculations you're interested in.